welcome you for this first session on the analysis of indeterminate structure. Before we start with the analysis of indeterminate structure, let us try to understand what is determinate structure, what is degree of indeterminacy, and then we'll try to understand how to analyze an indeterminate structure by developing an additional equation with the help of compatibility condition. Now, we can say the structure is determinate if the equations of equilibrium are sufficient to analyze the unknown forces in a given structure. If the unknown forces cannot be calculated with the available equations of equilibrium, then we can say it is a statically indeterminate structure. The simple example of a determinate structure is a simply supported beam. We have a simply supported beam which is subjected to a uniformly distributed load of W kN per meter. And we have two reactions at A and B. Now we have to calculate these unknown values of VA and VB with the help of available equations of equilibrium. Equations of equilibrium. Now, what are those equations of equilibrium? Or summation of horizontal force equal to 0, summation of vertical force equal to 0, and summation of moment about any joint is equal to 0. Using these three equations of equilibrium, I should be in a position to calculate the number of unknowns, which are VA and VB here. Now here, the number of unknowns are equal to 2, and the available equations of equilibrium. Available equations of equilibrium are also equal to 2, because here summation of vertical force equal to 0 can be applied, and summation of moment about any point A equal to 0 can be applied, whereas summation of horizontal force equal to 0 doesn't become a valid for this example which I have taken. Now the number of unknowns are equal to the number of available equations of equilibrium. So it is easily we can solve the simultaneous equation to calculate these unknowns or values of VA and VB. So hence we can say this is a determinate structure. So we can define that if we can able to solve the unknown values, unknown reaction values by using equations of equilibrium, then we can say it is a determinate structure. If not, then we can say it as an indeterminate structure. Now, if you want to take an example of a beam, which is one end is fixed support and the other end we have a roller support. We call this as a propped cantilever beam. Say if it is now, if I want to calculate the number of unknowns, I will have to calculate the number of reaction. At the fixed support, we'll have, if I designate this joint as A and this as B, I'll have a horizontal reaction at A, I'll have a vertical reaction at A, I'll call it as BA. Along with that, I'll have a moment that I will call it as MA. And since we have a roller support at B, we'll have a vertical reaction which is perpendicular to the plane of roller. I'll call it as BP. So the number of unknowns here are equal to 4, and the number of equations we have, the number of equations, the available equations of equilibrium, we can apply all the three equations of equilibrium, that is summation of vertical force equal to 0, summation of horizontal force equal to 0, and summation of moment about any joint equal to 0 can be applied. So we have three equations of equilibrium. So now I can say the degree of indeterminacy for this is equal to 1. Degree of indeterminacy is equal to 1. I can even say the static degree of indeterminacy is equal to 1. Now, what does it mean that if the static degree of indeterminacy is equal to 1? It means that we need an additional one more equation in order to solve the unknown values of these reactions. So now, if I want to calculate the degree of indeterminacy for a given problem, I should be in a position to calculate the total number of unknowns and the available equations of equilibrium. If the available equations are equal to the number of unknowns, then we can say that it is a determinate structure. If the number of unknowns are more than the available equations, then we can call it as an indeterminate structure. Now we can take up another example of a continuous beam. I'll take up and let us see. I'll make it one end is fixed. We have a roller in between, and we have another roller over here. I'll designate this joint as A, B, and C. Now, since it is a fixed support, we'll have three reactions. A horizontal reaction, I'll call it as HA, vertical reaction BA, and we'll have a moment at A, I'll call it as MA. Similarly, we'll have a vertical reaction BB, and I'll have a vertical reaction here BC. Now, the number of unknowns is equal to 3 plus 2, which is equal to 5, and the number of equations which are available are equal to 3. So now I can say that the static degree of indeterminacy is equal to 2. So it means that if I want to analyze this beam to calculate all the internal forces, I should be in a position to develop 2 more additional equations in order to solve the unknown values. Now I'll take up another example here, which is also a continuous beam. Let me consider this as a simple support. I will consider this as a simple support, and this also as a simple support. Now I'll designate this as joint A, B, and C. Now what I'll do is I will insert one more joint here. I will call it as joint D, which is an internal hinge. I will call that as an internal hinge. What I'll do is we'll have reaction at A, BA, I'll have reaction at B, BB, and I'll have reaction at C. So in this present problem, the number of unknowns would going to be equal to 3, right? A reaction at A, B, and C. Now the number of available equations is going to be equal to, we can apply summation of vertical force equal to 0 and summation of moment about a point equal to 0. These two are the equations of equilibrium, and we'll have an additional equation because of an internal hinge. What does this internal hinge does is moment about T equal to 0. That is, at that joint the beam is allowed to rotate, so because of which we have an additional equation. So that I will also add, so that I will have 3 equations, and we have 3 unknowns. So the static degree of indeterminacy for the given problem is equal to 0. So it is a determinate structure. It's a determinate structure. Now, whatever the degree of indeterminacy which we are calculating is, I would say it as an external indeterminacy. I would say it as an external indeterminacy. Why would I say it as external indeterminacy is because now we are trying to calculate this degree of indeterminacy based on the external reactions. That is why I'm taking it as the degree of indeterminacy as external. Now I will take another example and I will show why we are calling this as external indeterminacy. We will be in a position to understand. Now we are very much familiar with portal frames, which we usually analyze. That is an assembly of beams and columns. Now I will take a 2-story portal frame, which is rigid jointed frame. Now here, if I just see at the boundary condition which we have taken, I've taken at the base one end is hinged and the other is a roller. So the number of reactions would going to be at this hinged support. I'll have 2 reactions. One is the horizontal reaction and the other is a vertical reaction. And here also I'll have a reaction. If I say it as A and B, I will call it as VA and VB. So we'll have three reactions, three unknown reactions, and available equations of equilibrium are also three. Equations are also equal to three, but equilibrium equation, I'm talking about the equilibrium equation, are also equal to three, but it doesn't, we can, with this we cannot say that it is a determinant, but it is indeterminate to an internal degree. Why I'm saying is that if I just take draw a free body diagram of an individual member of this, if I just take this member and if I draw the free body diagram, there will be three forces which are acting. One is the axial force which is acting, and there will be a shear force B, and there will be a moment in the plane of board, there will be a moment which is acting. So each individual member will have three unknowns. So what I will do is the number of unknowns are equal to three times the number of members I will calculate, and then the number of unknowns are also equal to 3m plus r, because this the number of unknown reactions are also to be included in the number of unknowns. So this would give me the total number of unknowns. And the available equations, how do I calculate is that at each joint, I can apply a joint equilibrium of summation of horizontal force equal to 0 and summation of vertical force, and summation of moment should be equal to 0 at each joint. So what I can do is available equations, I can say it is 3 into G. Using this, I will be in a position to calculate the degree of indeterminacy for the problem which we have considered, which is a hotel frame, which is a two-story, sorry, it is a hinged support. We have number of members, I will call it as 1, 2, 3, 4, 5. Number of joints, 1, 2, 3, 4, 5, and 6. We have 6 joints. Number of joints are equal to 6. Number of members are also equal to 6. And number of reaction are equal to 3. Now I will calculate the static degree of indeterminacy is equal to the number of unknowns minus the number of equations. Number of unknowns are nothing but for each member we have 3 unknowns plus, and we have an additional reactions, support reaction, those are also treated as unknown values, minus at each joint I can apply 3 equations of it. Now if I just substitute, which is number of members are 6 plus the reactions are equal to 3 minus 3 into number of joints are also equal to 6. So now, so that you can say this 3 into 6 and 3 into 6 will get cancelled. The degree of static indeterminacy is equal to 3. So this is an internal indeterminacy. You can say it as internal indeterminacy, because the external reactions, we have only 3, and which can be easily basically equations of equilibrium are 3, we can easily calculate that, but since we have internal indeterminacy, we are unable to calculate the external reactions as well. So we can use this generalized equation of static degree of indeterminacy equal to 3m plus r minus 3j in order to calculate the static degree of indeterminacy for rigid jointed frames, which can be easily calculated. Now we have understood what is the degree of indeterminacy and how to calculate the degree of indeterminacy. Let us move on to next exercise, wherein we try to calculate what is, how do we develop an additional equation. As I mentioned, that if I want to analyze an indeterminate structure, we need to develop additional equations. Now, let us take this compatibility condition. We'll try to understand with the help of an example. Now, what I will do is I'll just take an example of a prop cantilever beam, which I had taken as an example to show it is an indeterminate beam. We have three reactions over here. I designate this joint as A, and B will have HA, BA, and will have a moment. I would call it as MA. Will have a reaction VB. Okay. Now, say let this member be subjected to a uniformly distributed load of W kilonewton per meter. Now, the degree of indeterminacy for this problem is equal to 1. So, we need to develop an additional equation apart from that of equations of equilibrium which we have. So, now what I'll do is I'll go with the help of a method of superposition. What is a method of superposition is that now what I can do is I can rewrite this beam, a propped cantilever beam, into a cantilever beam which is subjected to a uniformly distributed load of magnitude W kilonewton per meter, and which is subjected to a load of VB in the upward direction at joint B. Now, this beam, I can split it into two beams. One is a cantilever beam, which is subjected to a uniformly distributed load of magnitude W. Say the length of the beam is L, and it has got a flexural rigidity of EI, L and EI. This is also L. Plus, I will consider same cantilever beam which is subjected to a point load of magnitude V, which is also of span L. Now, what I'll try to do is we know that since this joint B is a roller support, the deflection, the vertical deflection at joint B should be equal to 0. It is this roller support will not allow the B at joint B to have a vertical deflection. Now I use that joint equilibrium conditions over here. That what I will do is because of the uniformly distributed load which is acting on the cantilever beam, this beam would going to deform in this fashion. Will have a downward deflection of delta, say delta 1. Now we have a reaction VB which is acting in the upward direction over here, which is creating the beam to sag and will have an upward deflection, and this I will call it as delta 2. Okay. Now this delta 1 and is in the downward direction and delta 2 is in the upward direction. Now we know that from the joint condition, the compatibility, it would say that the vertical deflection at joint B should be equal to 0. What does it mean? Is that delta 1 plus delta 2 should be equal to 0. So this is the compatibility condition by using a displacement. So I can say this as a displacement compatibility condition. And I'm calculating this delta 1 and delta 2 by splitting this beam into two separate beams. So what I'm trying to do is I'm analyzing the beam with one load and I'm calculating the deflection at joint B, and I'm also calculating another load at the same joint B. I'm calculating the displacement. So I'm calculating the displacement by superposing things. So this concept of calculating delta 1 and delta 2, we are doing that is nothing but the principle of superposition. Now, if I just calculate delta 1 and delta 2, I'll be in a position to find out the unknown values of reactions. So now I'll just recollect the things which we have learned at the elementary level of strength of material, that for a cantilever beam which is subjected to uniformly distributed load, the delta maximum, which would be at the free end, so delta maximum would going to be equal to W L to the power 4 by 8 EI for a span of L and for a load of W with a flexural rigidity of the beam to be as EI, this delta. And similarly, for a cantilever beam, which is subjected to a concentrated load at its tip with a span L and flexural rigidity as EI, now this again the deflection due to a load of P, a concentrated load, this delta value would going to be equal to PLQ by 3 EI. Now I'll make use of this delta values as we are analyzing this cantilever beam subjected to uniformly distributed load and point load. What I will do is I will say delta 1 is equal to WL to the power 4 by 8 EI, and similarly delta 2 is equal to WLQ by 3 EI. But what happens here is the point load which is acting, I am taking it as P. So here I have called it as VB, right? I will replace this as VB. So now, and this VB is acting in the upward direction, whereas the P which was taken was in the downward direction. So I will take this delta 2 as negative. So now applying this displacement compatibility, we'll get W to the power 4 by 8 EI minus VB into LQ. Now I will be in a position to calculate what is VB now. So VB would going to be equal to this EI will get cancelled. I'll have WL divided by 3 into W by 8. So this would going to be the reaction. This would going to be the reaction VB. Now we can calculate what is VA by applying summation of vertical force equal to 0. The total load which is acting is W into on a span of L which is acting WL. So if I take summation of vertical force equal to 0, that WL minus 3WL by 8 should be equal to VA. So I can directly write it as 5WL by 8. Once I know these values, I will also be in a position to calculate what is the bending moment which is acting at A. On the whole, we have understood what is a determinate structure, how to calculate degree of indeterminacy, and we have also understood how to develop additional equation in order to solve an indeterminate structure. In the next session, we will be discussing on slope deflection method to analyze indeterminate beams. Thank you.